In electrical and electronic systems, reactance is the opposition of a circuit element to a change in current or voltage. Due to that element's inductance or capacitance, a built-up electric field resists the change of voltage on the element, while a magnetic field resists the change of current. The notion of reactance is similar to electrical resistance, but it differs in several respects. In phasor analysis, reactance is used to compute amplitude and phase changes of sinusoidal alternating current going through a circuit element. It is denoted by the symbol. An ideal resistor has zero reactance, whereas ideal inductors and capacitors have zero resistance, that is, respond to current only by reactance. The magnitude of the reactance of an inductor rises in proportion to a rise in frequency, while the magnitude of the reactance of a capacitor decreases in proportion to a rise in frequency. As frequency goes up, inductive reactance goes up and capacitive reactance goes down. Capacitive reactance. A capacitor consists of two conductors separated by an insulator, also known as a dielectric. Capacitive reactance is an opposition to the change of voltage across an element. Capacitive reactance is inversely proportional to the signal frequency and the capacitance. There are two choices in the literature for defining reactance for a capacitor. One is to use a uniform notion of reactance as the imaginary part of impedance, in which case the reactance of a capacitor is a negative number. Another choice is to define capacitive reactance as a positive number. In this case, however, one needs to remember to add a negative sign for the impedance of a capacitor, i.e., this article uses the former definition throughout. At low frequencies, a capacitor is an open circuit, so no current flows in the dielectric. A DC voltage applied across a capacitor causes positive charge to accumulate on one side and negative charge to accumulate on the other side. The electric field due to the accumulated charge is the source of the opposition to the current. When the potential associated with the charge exactly balances the applied voltage, the current goes to zero. Driven by an AC supply, a capacitor will only accumulate a limited amount of charge before the potential difference changes polarity and the charge dissipates. The higher the frequency, the less charge will accumulate and the smaller the opposition to the current. Inductive reactance. Inductive reactance is a property exhibited by an inductor, and inductive reactance exists based on the fact that an electric current produces a magnetic field around it. In the context of an AC circuit, this magnetic field is constantly changing as a result of current that oscillates back and forth. It is this change in magnetic field that induces another electric current to flow in the same wire, in a direction such as to oppose the flow of the current originally responsible for producing the magnetic field. Hence, inductive reactance is an opposition to the change of current through an element. For an ideal inductor in an AC circuit, the inhibitive effect on change in current flow results in a delay, or a phase shift, of the alternating current with respect to alternating voltage. Specifically, an ideal inductor will cause the current to lag the voltage by a quarter cycle, or 90 degrees. In electric power systems, inductive reactance can limit the power capacity of an AC transmission line, because power is not completely transferred when voltage and current are out of phase. That is, current will flow for an out-of-phase system, however real power at certain times will not be transferred, because there will be points during which instantaneous current is positive while instantaneous voltage is negative, or vice versa, implying negative power transfer. Hence, real work is not performed when power transfer is negative. However, current still flows even when a system is out of phase, which causes transmission lines to heat up due to current flow. Consequently, transmission lines can only heat up so much. So transmission line operators have a ceiling on the amount of current that can flow through a given line, and excessive inductive reactance can limit the power capacity of a line. Inductive reactance is proportional to the sinusoidal signal frequency and the inductance, which depends on the physical shape of the inductor. The average current flowing through an inductance in series with a sinusoidal AC voltage source of RMS amplitude and frequency is equal to, because a square wave has multiple amplitudes at sinusoidal harmonics. The average current flowing through an inductance in series with a square wave AC voltage source of RMS amplitude and frequency is equal to, making it appear as if the inductive reactance to a square wave was about 19% smaller than the reactance to the AC sine wave. Any conductor of finite dimensions has inductance. The inductance is made larger by the multiple turns in an electromagnetic coil. Faraday's law of electromagnetic induction gives the counter EMF due to a rate of change of magnetic flux density through a current loop. For an inductor consisting of a coil with loops, this gives the counter EMF is the source of the opposition to current flow. A constant direct current has a zero rate of change, and sees an inductor as a short circuit. An alternating current has a time-averaged rate of change that is proportional to frequency. This causes the increase in inductive reactance with frequency. Impedance. Both reactance and resistance of components of impedance. Where is the impedance measured in ohms? Is the resistance measured in ohms? It is the real part of the impedance. Is the reactance measured in ohms? It is the imaginary part of the impedance. Is the square root of -1, usually represented by in non-electrical formulas. When both a capacitor and an inductor are placed in series in a circuit, the contributions to the total circuit impedance are opposite. Capacitive reactance and inductive reactance contribute to the total reactance as follows. Where is the inductive reactance measured in ohms? Is the capacitive reactance measured in ohms? Is the angular frequency times the frequency in Hz. Hence, if the total reactance is said to be inductive, then the impedance is purely resistive. If the total reactance is said to be capacitive. Note, however, that if and are assumed both positive by definition, then the intermediary formula changes to a difference, but the ultimate value is the same. Phase relationship. The phase of the voltage across a purely reactive device lags the current by radians for a capacitive reactance and leads the current by radians for an inductive reactance. Without knowledge of both the resistance and reactance, the relationship between voltage and current cannot be determined. The origin of the different signs for capacitive and inductive reactance is the phase factor in the impedance. For a reactive component, the sinusoidal voltage across the component is in quadrature with the sinusoidal current through the component. The component alternately absorbs energy from the circuit and then returns energy to the circuit. Thus, a pure reactance does not dissipate power.